Okay. So yeah, so one wants to enter a class. Okay, this way. Yeah. So basically, what the first law of thermodynamics gives. As we all know that the amount of energy, okay, so just like heat, so in a cyclic process the amount of energy which will be just consumed by that system will be equal to the amount of energy which will be released by the system. Just like that, the first law of thermodynamics actually it was set, isn't it? So amount of energy can neither be created nor destroyed, but it can be converted to one form of energy to other form of energy. Okay, so just like you can take the example, suppose one ball, okay, it is just rolling, okay, and now you are, what you are doing, you are just catching that ball, okay, metallic ball, by some metallic device. Okay, so when that ball is rolling, so what is happening, some work it is doing, isn't it? Let's say that amount of work is W. Okay, so when the ball is suddenly stopped, so what happens, so the ball will be heated, isn't it? Because due to the friction in between these surfaces which will be catching that ball, so it will produce some friction force, okay, or it will the whole kinetic energy will be converted to all those dissipative energy. Okay, and if that ball is insulated, so the heat will be generated, isn't it? And if you just measure the amount of work when it was rolling, or when it was moving, or when it was running, then if you measure the heat, okay, so that may be exactly equal. Okay, so W will be equals to Q. Okay, so it is possible. But if you do the reverse thing, suppose you just utilize that heat, okay, you just give same amount of heat, but you cannot get same amount of work, you cannot roll that ball. Okay, you may be able to roll that ball, or you may be able to run that ball, but it will not gain that much of velocity or kinetic energy as it was doing, okay, when it was rolling initially. Okay, so that second state, it is not exactly equal to the first state. Means when work was converted to heat, the work will be equivalent to heat. Okay, but when you are doing the reverse process, that same amount of heat you are just giving to the system and you are expecting same amount of work, it will not be possible. It will do some work, but it will release some heat at the same time. Okay, so work and heat are mutually convertible, but you cannot say that same amount of work will be means gained by the system by utilizing same amount of heat. Okay, so from that concept, actually Sadi Carnot, one scientist was there, so his name is Sadi Carnot, Sadi, Sadi, Carnot, Sadi Carnot. I think all of you have heard about Carnot engine, okay, or Carnot cycle. So Sadi Carnot, what he actually says that energy, okay, so energy can be divided into two categories. One is low grade energy, one is high grade energy. So heat is a low grade energy, okay, and work is a high grade energy. So Sadi Carnot defined work as a high grade energy and heat as a low grade energy. So that point is important. Okay, so the first law of thermodynamics, basically what it actually uh, gives, it actually it does not give any information on whether the change of a state or a process is at all feasible or not. Okay, the first law cannot indicate whether a metallic bar of uniform temperature can spontaneously become warmer at one end and cooler at the other end. Understood? But second law, what it says, so see, all the natural processes happens spontaneously in one direction. Okay, water always flows from higher elevation to a lower elevation, isn't it? So if you want to flow water from a lower elevation to higher elevation, so you are moving against the direction of nature, isn't it? You are moving against the law of nature. So you need to do some extra work. Okay, so in our home, what we generally do, so we pump water, isn't it, from lower elevation to higher elevation. So we need extra energy, so works needs to be done, okay, through the help of that pump, okay, so that water can flow from lower elevation to higher elevation. But naturally water will flow from what, higher elevation to lower elevation. Just like that, diffusion will always happens from a high concentration to a low concentration area, isn't it? So the reverse is not possible in nature, isn't it? So if you want to do in reverse direction, so you need to do some extra work, isn't it? So that spontaneity, it is given by the second law of thermodynamics, okay. So first law of thermodynamics, it can say that, okay, if one part is heated, then another part will be cooled, okay. But from hotter body, the heat will flow to the cooler body, or from cooler body, the heat will flow to the hotter body. The first law cannot say, okay. So it can only measure the amount of the quantity, okay, or it can say that the equivalent quantities can be determined, okay, or can be some parameters or some measurements can be taken by the help of first law of thermodynamics. But the second law of thermodynamics, it will give you the direction of the flow of energy. Understood? Okay. So to study the second law of thermodynamics, okay, so there are two statements basically given by Kelvin and Planck, and second one was Clausius statement. So we will see, okay, those two statements. So before that, so we should know what are energy reservoirs, okay. So energy reservoirs means what? Suppose in your pocket, okay, so if you are having coins, 1 rupee coins or 2 rupee coins of an amount of 1 lakh rupees, let's say it is not possible in one pocket 1 lakh rupees coins, okay, of 1 rupee coin, it is not possible to carry. But let's say one bag it is there where 1 lakh rupees there of 1 rupee coin, okay, means 1 lakh 1 rupee coin will be there. Suppose one coin it is dropped out, okay, or it falls down, it is fell down, okay. So will you say that there are 99,999 rupees? So you won't say like that, okay. So almost you can say that there are 1 lakh rupee, okay, in that bag, okay, which is equivalent amount to 1 lakh rupee, okay. So just like that, energy reservoirs are the systems which are having large amount of heat capacity, okay. Means suppose your river, so river is a energy reservoir. So from that river, okay, from one river, if you just take out one bucket of water, so will you say that one bucket of volume is used from the river? So you won't say like that, isn't it? So just like the example of 1 rupee coins, okay, in a single bag, when it is dropped out, one coin drops out, so you won't say that there is less than 1 lakh, but you will say that this is approximately 1 lakh rupee, isn't it? So just like that, the energy reservoirs behaves like that only, okay. So it is having infinite heat capacity, okay. Suppose if you are taking q1 amount of heat from that energy reservoir, the total amount of heat it will be constant in the reservoir, okay. There will not be any change of temperature. Understood? So if you are giving some amount of heat, okay, so there will not be any change of temperature. Understood? Then the other reservoir is called as mechanical energy reservoir, so where mechanical energies are stored, okay. Means example of this mechanical energy reservoir, it is flywheel, okay. Basically these flywheels are used in automobiles, so in some diesel engines also, diesel or petrol engines also they are used, so you might have seen these flywheels, okay. So these are mechanical energy reservoir, okay, so which can store potential energy as well as kinetic energy. Understood? So whenever the system will need, so it will provide those energies. Understood? Yeah. So uh, so first we will be studying this cyclic heat engine, okay, cyclic heat engine or heat engine cycle. So what is a cyclic heat engine, or what is a heat engine? So basically your automobile engine, it is also a heat engine, okay. This generator, electric generator, they are also heat engines. So basically they operate in a cycle. Okay, so what is a cycle? So in thermodynamics we have defined cycle like that. So if the initial and the final states are same, okay, or alike, then we will say that the thermodynamic system is in a thermodynamic cycle. Understood? So here it is defined: a heat engine cycle is a thermodynamic cycle, okay, in which there is a net heat transfer to the system and a net work transfer from the system. Okay, so the system which executes a heat engine cycle is called a heat engine. Understood? So when initial condition and final conditions are same, the system will be doing some processes, isn't it? So in those processes, so in some processes heat will be taken by the system, and in some processes work may be done by the system. But finally what you will get, you will see that the initial state and the final state of the system are same. Okay, system is same. So a engine which executes a heat engine cycle is called a heat engine. So what is a heat engine cycle? So we will see. Okay, so what is, all of you, I think all of you know what is a heat engine cycle, because I assume that all of you have watched those videos. Okay, yeah, the efficiency of this heat engine, it is called as thermal efficiency. Okay, so you need to remember that thing. The efficiency of a heat engine which undergoes cyclic heat engine cycle, so that efficiency is called as thermal efficiency. And the definition of this efficiency is given as net work output of the cycle. Means net work, just you remember this one, W net by Q1. So why this is W net by Q1, so we will see now. Understood? Yeah, just wait. Yeah, just wait. Okay, so heat engine. So here you are able to see two diagrams, A and B. Okay, so what is A? We will go one by one. Just wait. uh, my voice is audible to you? Anyone please respond?
Yes, sir.
Yes,
Okay.
sir.
Yes. Okay. Okay. So basically these are two examples of heat engines. Okay, so what are they? I will tell you. So this is a piston cylinder arrangement. Okay, so in 2D it is drawn. So this is cylinder, outer periphery, it is cylinder, and this is the piston. So what actually we are going to do, so we will be performing one cycle. Okay, means this is one engine. Let's say this is one engine. Okay, piston cylinder engine, because what happens in our motor vehicles engine, there will be one cylinder and a piston arrangements. Okay, so in between this piston and cylinder, so our petrol and diesel, it is burned, isn't it? So basically what we are getting, we are getting some work, or we are getting some power. Okay, just because we are getting power means some work it is done by the engine. Okay, so there is a heat engine, that is why this basic component it is taken here. Okay, and this is example of heat engine. Okay, so how the cycle will happen, why it will be a heat engine? Because the process will be a heat engine cycle. So how this process will happen, I will tell you. Okay, so see, uh, uh, this cylinder, piston cylinder arrangement, so the fuel will be there, isn't it? So the fuel will be there. So what will happen? So the system will take heat. Okay, so the system will take heat, and will what it is done here, when the system will take heat, the molecules will collide. Okay, so there will be intermolecular energies. Okay, so what they will do, so they will just exert some pressure on the piston surface, outer surface. Okay, means it will be inner surface of the piston. Okay, so they will push the piston to the right hand side. Okay, so that is why W is written, means work of expansion. So expansion work it is there, so means this volume will be increased. Okay, so earlier the boundary it is this one, now the boundary will be expanded. So Q1 is the amount of heat which it is absorbed because it is heated. Okay, and WE it is the amount of work done. Okay, so this is let's say process 1. Okay, in another process where the piston, okay, so where work it is done, because we need to compress the piston, we need to make it a cyclic process. Cyclic process means what? Whatever be the parameters of pressure, temperature, all those things, so we need to regain all those things exactly same as it was there initially, isn't it? So what we need to do, we need to just compress this piston, isn't it? So when we compress this one, so we must have to do some work from the outer part, isn't it? So WC is the compressive work which it is done. So as it is compressed, so again the system will be gaining the same temperature, pressure, and all those things, isn't it? And at the same time heat will be released. Okay, means Q1 amount of heat it was absorbed, it absorbed, and WE it did the work. And now to the from state 2, because now this is state 2. Okay, so from state 2, if we want to gain the state 1, then we need to do some of WC, and we have to release the heat from the system. Then only you will get as same temperature, same pressure. Okay, means you are doing a cycle. Okay, so in this cycle, so if you just want to apply the first law of thermodynamics, what it is said, so the amount of, okay, means summation of the heat transfer, okay, means Q1 minus Q2, because these are two. If you just apply the sign convention, so Q1 minus Q2 will be exactly equal to W net, means in a cyclic process, the amount of heat will be equals to the amount of summation of work. So there are two work interaction. So if you just add these two, that will be exactly equals to this Q. Okay, so Q net, Q1 and Q2. Understood? So if you just apply the sign convention, then you will get the exact values. Understood? So that is the first law of thermodynamics applied to the system. Okay, so now for this system, what actually again, I will tell. Then the second system I will elaborate. Then we will find out the thermal efficiency of these two system. Okay, I think this figure is understood to you. Now let's say this is one steam power plant. Okay, so all of you have heard about a power plant. Okay, until now you have come to know the terminologies like pump, condenser, okay, turbine you have also. Okay, so the diagram, okay, by which you will show a turbine will be this one. Okay, means trapezoidal form. In this trapezoidal form, so you will be showing this tapered form you will be showing a turbine. Okay, always you will draw this type of diagram when you are showing a turbine. Okay, so for pump, this is the diagram. Understood? And this is a condenser. Condenser is what? Suppose some steam it is there. So if you just condense the steam, so what will happen? So the steam will be converted to water, liquid. Okay, so that is a condenser. So condenser converts vapor into liquid. Okay, so heat will be released in this process. Otherwise, if because vapor it is in a higher temperature, isn't it? So if you just maintain lower temperature, if you just apply ice on the periphery, so what will happen? So the vapor will condense, isn't it? So water you will get in the pump. So that concept it is there. So this is a steam power plant. Okay, and what it should be? It should be a heat engine. So what is a heat engine? So the engine, heat engine, which the engine which actually possess cyclic heat process. Okay, or cyclic heat engine cycle. Heat engine cycle, if it possesses heat engine cycle, then it is a heat engine. Understood? So how the cycle it is performed in a steam power plant? So uh, some heat, okay, from the furnace, so coal will be burned or some fuel will be burned, so heat will be taken by this boiler. So here liquid will be there, water will be there. Okay, water is flowing through these pipes, okay, through this turbine, through this condenser, through this pump, water is flowing continuously. So this water will take heat, okay, from this furnace, means some high temperature it will be introduced, okay, to this boiler. Then what will happen? The water will be heated, okay, and this water will be converted to vapor, isn't it? So the vapor will be flowing at a high pressure and it will be going to this turbine. Okay, so what this turbine will do? So this vapor will strike in the blades of the turbine. In turbine, there are numbers of blades which are fitted parallelly, okay, inside this turbine. So what will happen? So the blades will rotate with a very high velocity, 5,000 rpm, 6,000 rpm, like the 10,000 rpm, okay. So generally it is said that to stop a turbine blade, okay, automatically you need 3 to 4 days, okay, 3, 4, 5 days. So frictionless blades are there, okay, on some axle, and it will be rotated, okay, because these vapors will be striking the blades of this turbine, okay, with a very high velocity, okay, high kinetic energy, and that is why the turbine blades will rotate. So when these turbine blades will rotate, what happens? So there will be a shaft which will be connected through this turbine blade, okay, and this shaft will rotate a generator here, okay, on the outer part. So this is a electrical system, that is why it is not connected here, okay. Only the work, okay, or the power which is produced by this turbine, it is shown, okay, by this arrow mark. This is WT, means work, it is done by the system. You are getting some work from this system, okay, to the surrounding. So this is positive work, WT, understood? So the steam which is there, so now it will just comes out, okay, and this will be condensed in the what condenser. So when it is condensed, so it is converted to water, isn't it? So some heat it will release, that is why it is converted to water, okay. So vapor, when it converts to water, so when the temperature it is released, isn't it? So the temperature is released as Q2. Earlier Q1 amount of heat it has taken, the water takes, okay. Now Q2 heat it rejects, okay. Means what? So it is trying to move to the initial state, okay, means the water temperature of water will be same, okay, when it is pumped again with this line, and again it is sent to the boiler. So from here, okay, to here the temperature it is increased. Now from here to here the temperature again decreased, and again it is reaching the same temperature T1, okay, means you are getting one cyclic process, okay. So here also in this engine, okay, heat engine, you are getting a cyclic process. Here also you are getting a cyclic process. That is why these engines are basically, these are engines, so as because they are following some cycles, so heat engine cycles, so they are called as heat engines, understood? They are engines as because they are following cycles, they are heat engines, understood? So all these things it is written. So for these two diagrams, so Q1 was the amount of heat was absorbed, Q2 is the amount of heat released, and for this boiler, Q1 amount of heat it is absorbed and Q2 is released, isn't it? So what is the net heat transfer? Then Q1 minus Q2, understood? Because it is positive, it is negative, okay. So if you just apply the sign convention, because heat taken absorb it is positive, heat release it is negative, Q1 minus Q2. Now what is work? So here you can see that net work transfer in a cycle, so it will be WT, because I have said that this is positive, you are getting some work, and here in the pump you need to introduce some motor, isn't it? To run a pump you have to introduce some motor. In house you are introducing one motor to the pump, okay. That is why you can run the water from low elevation to a second floor or third story building, isn't it? So works needs to be done. So total work will be WT minus WP, understood? So WT turbine, this is a big component, very big component, okay. That is why this work output will be very high in comparison to this motor, okay. So WT minus WP. So what first law of thermodynamics says? So this, in a cycle, the net amount of work, means W net will be equals to Q net, okay. So that is first law, but we are going to study the second law, okay. So here, yeah, you can see that first law, the summation of Q will be equals to summation of W. Why you are able to write this? Because they are following some cycles, okay. So here instead of Q you are writing Q1 minus Q2, so WT minus WP. So basically we are going to find out the thermal efficiency, okay. So here this is the same as I have told you, that the heat pump efficiency, it is denoted by a thermal efficiency, and this is defined as the output by input, okay. So what output you are getting? You are getting work. Everywhere you are getting what? So here you are getting some net work output, and here also you are getting some net work output, because for a steam turbine, steam power plant, what is the output? So we need to produce electricity, and due to this work output only you are able to find out the electricity. Okay, means you are generating electricity with the help of this work output. Understood? So here also in an engine, because of this work, we are getting the power. Okay, and that is why you are able to run your wheels. Okay, so W net divided by Q1. Why it is Q1? Because the input heat was how much? For both these cases of this heat engine, earlier Q1 is the amount of heat it was absorbed, and you are getting some QW net, and here also Q1 amount of heat you are actually applying to the system, and you are getting some W net. It is why the wheels are run, okay, for this vehicle. Okay, so Q naught by Q net, W net by Q1. So what is W net? So for this steam power plant, WT minus WP, isn't it? So work done by the turbine minus uh, work done by the turbine minus work is done on the pump. Because work is done on the pump, you are applying motor. Okay, you are introducing motor. So on motor, work needs to be done, but in turbine, work it is done by the turbine. So the WT minus WP by Q1. Okay, so what is WT minus WP? Because in a cycle, the total summation of work will be equal to summation of heat, isn't it? So Q1 minus Q2. So directly you can write from here, Q1 minus Q2 equals to WT minus WP. Okay, so Q1 minus Q2 by Q1. So if you just arrange these terms, so Q1 by Q1, it will be 1 minus Q2 upon Q1. So this term will be remain this one. So from this term, so what you can say, what you can conclude, that since heat Q1 transferred to a system cannot be completely converted to work in a cycle, so W net, okay, W net will be less than Q1. Okay, so as I have told you that by this first law, what you can say, that W can be converted equal to an equivalent amount of Q. Okay, but Q cannot be converted to an equivalent amount of W. In both the cases, what is happening? So Q it is taken and W it is producing. Okay, Q net Q1 it is taken, W net it is producing. So that is why, so W net is always less than Q. Okay, so Q is greater than W net. So Q1 is greater than W net. That is, it is written. Okay, and here you can say that if eta was 1, that means what? The engine has a 100% efficiency. Okay, but here Q2 is not 0, isn't it? Here this Q2 it is having some definite value. That is why the water it is condensed. So here Q2 is having some definite value. Okay, that is why 1 minus some definite value will be always less than 1. So this right hand term will be always less than 1. That is why thermal efficiency of a heat engine cannot be equals to 100%. So this is the reason, and this is the analysis. Okay, so this is the mathematical expression by which you are able to prove that thermal efficiency of a cyclic heat engine cannot be 100%. It will be always what? Less than 100%. Okay, so that is why engineers are doing work on engines. Okay, different companies are manufacturing different engines so that they can increase the thermal efficiency. Basically the efficiency is 30 to 35% for SI engine and 35 to 40% for diesel engines. Understood? So for C, petrol engine 30-35, diesel engine 35 to 40%. Okay, so just like that, and 60 to 65% for modern gas steam power plants. Okay, gas steam power plants. So gas power plant or steam power plant. So this is the efficiency. So engineers have always the scope to increase the efficiency. That is why, so day by day you will see newer engines. Okay, means innovative engines for innovative vehicles. Okay, so there is a scope of increasing the efficiency. Okay, by introducing turbocharged engine. Okay, so like other types of technologies are also there. Okay, so this is all about your heat engine. Okay, so after that what we will do, so what you have seen that in this heat engine, so from some source, okay, from some source the heat is taken by the system, and at some source the heat is rejected. Okay, and in between work it is done by the system, or work it is delivered by the system, isn't it? So this is actually, this implies the statement, okay, of Kelvin Planck's of second law of thermodynamics. So what is that? So it is impossible for a heat engine, because we have studied heat engine. So it is impossible for a heat engine to produce network in a complete cycle if it exchanges heat only with bodies at single fixed temperature. Means this sentence, though this sentence, it is a little bit tough to understand, but if you just go to each and every word, then it will be clear to you. Means what? So the heat engine will always produce some work, okay, only if the heat engine, because this is heat engine and it is shown by cycle, as because this is cyclic heat engine. So if it exchanges heat with two reservoirs, from one it is taking heat and to another it is rejecting heat, okay. So if this part it is removed, so this is not a heat engine, okay. So this type of machine does not exist. So that is what it is actually said by this statement. It is impossible to construct one heat engine which will produce work when it will share or when it will take heat from only from one source or bodies at a single fixed temperature. Means it needs to take heat from one source and it needs to reject it to another source, then only the heat the work will be produced by this system. It is not possible interacting only with one source, okay. Means this type of engine it is not possible. See here, q1, the heat engine, cyclic heat engine, it is taking q1 amount of heat and it is producing w net, okay, and it is not rejecting any heat to anywhere. So this type of machine is impossible. That is why it is called as perpetual motion machine of second kind. The perpetual motion machine of first kind we have studied in first law of thermodynamics. Here this is perpetual motion machine of second kind. Understood? So this is not possible. PAPMM2 machine, it is not possible. So what is it is written actually by Kelvin Planck statement, that Kelvin, it is impossible for a heat engine to produce net work in a complete cycle. In a cycle it is actually undergoing if it exchanges heat only with a bodies at a single fixed temperature. If it exchanges heat only with one temperature source, okay, it means what? It needs to reject heat at another source, then only it can produce W net work. Because in all those examples you have what you have seen, that Q1 amount of heat it is taken, it is producing W net when it is rejecting heat Q2. If this part it is not there, it cannot produce Q1 amount of heat and WT amount of work. Understood? At the same time it needs to reject some heat, okay. So here also it is taking q1 amount of heat and it is doing W net when it is rejecting heat q2. Understood? So if it is not rejecting heat q2, so this WC will not exist. Understood? So just like that. So this is all about Kelvin Planck statement, okay. So another statement it is there. So yeah, so what is the value? So q1 minus q2. So W net is what? For our examples, it was WE minus WC and WD minus WP, work done by the turbine minus work done by the pump. So that is exactly equivalent to q1 minus q2, isn't it? Because or by first law you can write W net equals to q net, okay, for cyclic process. So this is cyclic heat engine. So heat engine is there. Another is heat pump, okay. Another is heat pump, because you need to define the Clausius statement, okay. So to define Clausius statement, or to have the knowledge of statement of Clausius, so we need to define what is a heat pump. So we will see this heat pump in the next lecture, okay. So dear students, are you able to understand what is this Kelvin Planck statement of thermodynamics, or is
Yes,
there
sir.
any doubt? I think now it is clear to all of you,
Yes,
isn't
sir.
it? And now you have got
Yes,
some
sir.
idea what you need to write actually on your copy, okay. And I will be sharing the notes, okay. So see, when I am just because this second law of thermodynamics, sometimes it is actually intermixing like things, okay, because Kelvin is saying some statement, okay, but the construction of the statement, it is little bit difficult, and Clausius, it is also saying something, but the summary is the same, okay. And finally we will see that Kelvin Planck statement and Clausius statements both are same, okay. If you violate Kelvin Planck statement, Clausius statements will also violate, like that it will happen. So we will see those things, okay, in the next class. So by next class, your second law of thermodynamics, it will be over, okay. And after that I will give some assignment, okay, some questions, okay, and notes also I will be sharing with you, and then it will be very much clear to you, okay, and you won't forget throughout your life, okay. So okay, then you can leave if you don't have any doubt. Thank you, dear students, for listening.
Thank you, sir.
Thank you, sir.
Thank you, sir.
And complete the work, okay, what I gave yesterday, please, okay, because I need to make one report on that.
Okay,
Yeah.
sir.
Hmm.
Thank you, sir.
Sir,
Yes, Rishikesh.
sir, more mane email moi
Thank you,
sir
sir.
itu sir moi email itu NCC document to পোৱা নাই sir. Itu WhatsApp দিব পাৰিব নেকি sir?
NCC document মানে?
Sir, itu যে যোৱা কালিৰ যে হিটো sir মানে ফৰ্মটো যে fill up কৰিব লাগিছিল